All right, welcome. In today's video, we're going to look at differential equations with resistive forces. We're going to do two examples. The first one's going to be if you have a car that's initially moving with some speed v naught, and it's going to slow down to rest due to air resistance, which is a type of resistive force. This resistive force is going to be defined as negative kV, where k is some constant and v is the instantaneous speed of the car at any given moment. So we have a few different things here we're going to be asked to do. Sketch a graph of velocity as a function of time. We're going to write but not solve the differential equation. And then we're going to go ahead and use integration to solve the differential equation. So let's first focus in on sketching the graph. So if we're sketching the velocity time graph, we know that we can figure out the beginning and ending points just by analyzing the problem. So I know starting off with the speed v naught, it's going to slow down to rest. And I know this has to be a natural exponential that's going to approach a flat constant velocity, in this case 0. I actually could also write my answer to part C, skipping the integration, which we know is going to be a natural exponential, by recording the maximum value and the fact that this is an exponential decrease. And in previous lessons, we learned about how to construct this equation. We'd have to sub in for tau, which we have to write out the differential equation in part B in order to figure out what tau is. And again, that was done in a previous lesson. So let's move on to part B. We're going to write the differential equation. So in this case, we're not solving it, we're just writing the differential equation. So we're going to start with the free body diagram. So if a car is moving, there's going to be only one horizontal force, and that's going to be due to the air resistance, kV. So if we write out our equation, which is our Newton's second law force equation, then we get negative kV equals ma. But of course, to make this a differential equation, we have to switch out this variable a with its differential. And that's because a is changing. As the speed slows, then the net force is lesser, and that makes the acceleration lesser. So that's why we're going to write this as an instantaneous rate of change for velocity, meaning it's differential dv dt. So this is actually our differential equation and the answer to part B. In order to move forward with this to get our time constant or to start to answer part C, we are going to isolate or rearrange this so that v is its own term. In this case, you actually would be isolating v, but it's not necessary to get v on its own side of the equation. We just want to get v as its own term, meaning we got to get rid of the negative k. And in doing so, this would be the form that we're going to move forward with. And this m over k would be our time constant tau on the previous slide. So now we're going to move on to part C. We're going to start with this equation where we left off. And we need to separate integrate. So this is going to be where we do part C using integral calculus. We're going to show where that natural exponential comes from. What I mean by that is we have to get dv and dt on opposite sides so we can integrate both sides. So I'm going to get m and k to the other side by multiplying by the reciprocal, k over m, and the negative sign as well. I'm also going to multiply by dt, which brings it to the other side. So k and m are constants, so those are easy to integrate with respect to time. I need to move the v, though, over to the side that has dv so I can integrate it, and that's where we get 1 over v, because I had to divide both sides by v to get it to the other side, so it's on the same side as dv. Now I can integrate both sides, and that will solve this problem. It's always important on the AP exam to put limits in on our integrals. So if we don't really have limits and we're just kind of starting at 0 and ending up at some value t, that's good to use as limits. In this case, we're going to start with an initial velocity v naught and end up with some speed v, which could be 0, but I'm going to let it be at some in-between speed where it's not 0, but it's not at that v naught. So it's somewhere in between the beginning and the end at some speed v. After we integrate this, integral of dt is t. When we subtract then 0, we get 0, right? When we sub in 0 for t, we get 0. And so we're just left with k over m, the constant, times t. On this side, 1 over v, when you integrate that, you get natural log. So when we sub in v and v naught, we get natural log of v minus natural log of v naught. We can rewrite this natural log in fractional way here, which will make our life a little bit easier to do some of the rest of the math that we have to do. So to get rid of the natural log, we're going to use that base e. So e to the negative k over mt. We'll then get rid of the natural log on this side. And of course, we can multiply both sides by v naught, and that will solve this expression for v. And that is the same answer that we had in our first slide, that we could construct using the max velocity and the decrease function. So we're going to look at example 2 now. Example 2 is going to be where we have a mass that's being released from like a very tall height, maybe a very tall building, at time equals 0, and it's going to experience a resistive force defined by negative bv. Just like k, b is going to be a constant. And what we're going to do is determine the terminal velocity, sketch the graph, right, but do not solve the differential equation, and then we're going to use integral calculus to solve it. So first, let's start with the terminal velocity. This is always going to be easy stuff. I mean, like when you're asked for determine the terminal velocity, get really happy because this is never a super complicated thing. It always occurs at equilibrium. So we're going to do a balanced force problem and solve for t. So let's go ahead and get at that. We're going to then do a force diagram. So we have BV, we have mg, and this is going to be when it's at equilibrium, meaning there's no acceleration, balanced forces. So mg is equal to bv. And at this situation, that v is going to be the terminal speed. So because the terminal velocity means it's a constant speed when these are balanced, it's grown in velocity and therefore had a bigger force until the arrow for the air resistance has grown to the same length as the gravity force. And at that point, then there's no more acceleration, so there's no more change to your speed. Solving for the terminal velocity, we get mg over b. If we want to sketch the velocity as a function of time, again, we're going to just think about what's the beginning point and what's the flat constant velocity that we're going to approach. So here we're going to start at 0 because it's released from rest, and then we're going to end up at that terminal velocity eventually at the end. And so that is going to be our natural exponential. And of course, I could also create the natural exponential function that will be our answer in part D by just knowing the max velocity. I'm sorry, the maximum velocity, and it's an increase, an exponential increase. And so we can use this expression to check our answer to part D that we'll do later. Moving on to part C, we're going to write the differential equation first, and then we'll integrate it to end up with this solution. So we're always going to start with Newton's second law to do this, which requires us to do the free body diagram. In this case, we do have two forces. We have mg down and bv up. And I'm drawing it slightly shorter to show that we're somewhere in between when it's released and before it's reached terminal velocity. So at that point, this bv is not going to be balanced with mg because it hasn't reached that flatline steady state of motion. So in this case, when we write out our Newton's second law force equation for the vertical axis, we get mg down because our acceleration is down. We make that direction positive always. Minus bv, that's up, and that equals ma. But of course, because the net force changes as velocity changes, your accelerations are going to change in response to that. So we're going to replace the a, again, with its differential, dv dt, and now we have our differential equation. As in the previous problem, if we wanted to move forward to get the time constant, or to solve this differential equation, we'd want to rearrange this so that v is its own term. That means we got to get rid of that b. And so if we divide everything by b, we end up getting mg over b minus v equals m over b dv dt. This negative sign should not be there. Now, starting with this one, we got to figure out how we're going to solve this. It's not as straightforward as the previous problem. So we have to go ahead and do a u substitution. So in the previous problem, we were able to solve it. If you can't solve it, then we're going to go ahead and do a u substitution. We're always just going to let, because it's in this format, the left side be u. So if we let that makes the decision making a lot easier for this. So when we when we let u equal mg over b minus v, we have to then define our du. So we're going to take the derivative of this first with respect to v, get negative 1, right? Because the derivative of this constant is 0. Derivative of v is negative 1. And that means dv is going to be equal to negative 1 du. So now we're going to replace this with u, and we're going to replace dv with negative 1 du. And that brings that negative sign that we saw on the previous slide that shouldn't have been there. That brings that negative sign out. If you notice here, this is the exact same format we had in example number 1, which means that now we can solve it the exact same way that we did number 1. And that's the beauty of rearranging this expression, because if we do have to do u substitution, we always can just make it the left side, and that takes the decision making out of the mathematical portion and allows us just to go ahead and solve this via the u substitution. So now, starting off where we left off, we're going to do the exact same thing. We're going to separate and integrate. We have to get the constants on the left side with dt, so I'm going to multiply by the reciprocal, negative b over m, and dt. I have to get u to the same side as du, so I have to divide both sides by u. I'm going to go ahead and integrate both sides, and by putting the limits on the integral, again 0 to t, here I'm not going to do v naught because I have u, so I got to do u naught and u. I'll have to replace those later because I'm not sure right now what u naught and u are, but I could figure that out when I need to later on. When I integrate these, the integral of dt is t, so when I substitute t in for that, we have negative b over m times t. And when I substitute 0 in for t, you just get 0. And of course, we get the natural log of u minus the natural log of u naught on the right side. Not sure if you can see this. I'm going to move myself over here for a moment. So now we have negative b over mt, the same thing we left off, but I'm just going to write this natural log in its fractional form. To get rid of the natural log, we're going to use the base e raised to the power of negative b over mt, and then that gets rid of the natural log on the right side. We can multiply both sides by u naught. And I need to replace these now with what they're equal to in terms of my velocity and original equation. So if you remember, I let u be equal to mg over b minus v. So when time 0 is occurring, the v is 0. So u naught is just going to be mg over b. U, at some later time, is actually going to have a velocity, so it would be this entire thing that we see here. So substituting those in, you can see u naught is simply mg over b because the v is 0, and then I substituted in the whole thing with v because at some later time there would be a velocity. As we move on, we're going to go ahead and solve this for v, and we do in fact get mg over b times 1 minus e to negative b over mt, which is exactly what we expected in our original approach here. I hope this was helpful. Let me know if you have any questions. Have a great day.